Okay, we're going to look at the tangent theorem and the radius and chord theorem. We did some constructions last year that proved some of these things. Probably don't remember, but we're going to go through and use them and just give you guys an idea of what this looks like. Some of this didn't copy very well, so I'll try to explain as I go. Maybe if I zoom in a little bit more, you can see some of this fine print. A secant line is a line that intersects a circle at 2 points. So they have this circle with the line drawn through. You can see 1, 2 points, and it's labeled secant line. A tangent line is a line that intersects a circle at 1 point. And so it just barely touches the circle and then goes on its way. You can think of a tangent as being like you're swirling something through the air, like maybe you're lassoing something, and when you let it go, it doesn't really follow the circle anymore. It goes off into a tangent line. That's where that phrase comes from. All right, so let's talk about the tangent theorem first. So you have a whole box that says tangent theorem that is blank. We're going to fill that in. So it says if a line is tangent to a circle, then the line is perpendicular to a radius of the circle drawn to the point of tangency. And we're going to draw a little picture. And I'm sorry about my handwriting. I'll read this again. If a line is tangent to a circle, then the line is perpendicular to a radius of the circle drawn to the point of tangency. So if you have a circle, draw the best circle that you can, and there is what we call a point of tangency, where this line over here is just going to intersect one point of the circle. What they're saying is if I draw a radius to the center of the circle at that point, it will be a right angle. It's going to be perpendicular. Okay? And that's going to help us with the next few problems, because if you draw some more lines and make a triangle, then we'll have a right triangle and we'll be able to use some right triangle theorems that we've already seen. So it says in each figure, line AB is tangent to circle O. There's supposed to be a circle symbol there. Looks like a circle with a center. Anyway, it didn't print for some reason. Find the value of x rounded to the nearest tenth. So what we have in here is AB is tangent to circle O. They drew it so that the line's a little further this way than this way, but remember it goes forever. Here's our point of tangency. So what we know, if this is a radius and this is a point of tangency, is that this is a right angle. And we can use all of our right triangle stuff to figure out this side. And if we look, 5 and 8 would be the legs, and x would be the hypotenuse, and we can go back and use the Pythagorean theorem, which you all know, I hope, pretty well by now. So we'd have 5 squared plus 8 squared equals x squared, which is 25 plus 64, which is 89. So 89 equals x squared. So to get x by itself, we would square root both sides. And 89, we're just going to go ahead and use a calculator approximation. It says to round to the nearest tenth. And so if you type that in and round it off, it comes out 9.4. And we don't have any labels as far as inches or centimeters, so I'm not going to worry about that for this example. Okay, pretty straightforward. It gets a little more exciting. So notice they've done this nice little bracket to show you that x is the whole thing. They don't always do that. So on the next one it says, again, line AB is tangent to circle O. The circle symbol's missing again. Find the value of x rounded to the nearest tenth. And so x in this case is just this little piece right here. You might take a highlighter or something to just let yourself see. We're just looking for that little piece. And so you might be going, how are we going to do that? Well, we know from here to here That's from the center of the circle to the outside. That's a radius, and the radius over here is 20, which means this part is 20 also. So if I solve for this whole hypotenuse, because this is where my right angle would be, then I can subtract that 20 and get that little piece left over. So it's just a little extra step. So I'm going to start by just using the regular old Pythagorean theorem. 20 squared plus 21 squared equals, and I'm going to call this whole side y squared. Why not? So if you want to mark that this whole thing is y, or you can just keep that in mind. Or you could call it c and just think of it as the hypotenuse. So 20 squared is 400, 21 squared is 441, and that equals that whole thing, which ends up being 841 equals y squared. And we get rid of the squared by square rooting both sides, and that one comes out an even 29. So remember that that means this whole thing is 29. So if you want to get rid of the y on there and write 29, that might help you. From here to here, we know that the radius is 20, because the radius is going to be the same all the way around the circle. Any radius that I draw, all of them would be 20. So if I take the 20 off, that'll give me the part of the triangle, that hypotenuse that is outside the circle. And so x is going to be whatever 29 minus 20 is, which is 9. Okay? So a little bit of a twist there. Let's take a look at the next one. So same basic directions. Line AB is tangent to, symbol's missing, circle O. Find the value x rounded to the nearest tenth. So this time they kind of put a bracket and they're showing you that x is just this piece out here. But we know if this radius over here is 8, that this one is also 8. So that little piece is 8, and we'll be able to work that out. And this is where my right angle is, because that's where the radius hits that line of tangency, the tangent line. So we'll start with just the Pythagorean theorem. 8 squared plus 25 squared equals, let's just call the whole thing c this time, c squared, the whole hypotenuse. We have 64 plus 625 equals c squared. We'll get 689 equals c squared. If we square root both sides, we'll get, it says round to the nearest tenth, so if you round that off, it becomes 26.2 for the whole thing. And then what we have to remember is we just want this part that's outside the circle, so we're going to take that 26.2 and subtract 8 from it, which gives us 18.2 for just that piece that's labeled x. Sorry, I went off the screen a little bit. Let me show that to you. So we just subtracted this 8 from this whole thing, which we found out was 26.2, to get the part that was on the outside. So that's the tangent theorem. I think it's pretty straightforward. Mostly it's just Pythagorean theorem, and then using a little bit of common sense if they're asking for this little piece out here. If they're asking you for the piece on the inside, you wouldn't have to do anything because they'd just be, you know, the same. But if this piece out here is what they're looking for, it's just a little Pythagorean theorem and some subtraction. All right, so next we're going to look at the radius and chord theorem. And so it's a little shorter than the other one. It says a radius that is perpendicular to a chord of a circle bisects the chord. And we talked about the word bisects last year. It means it cuts it in half. So we'll draw a little circle down here. So we have a radius. So let's draw that radius just straight up to the top. And if it is perpendicular to a chord. So a chord is just one of those segments that goes across like this. Talked about it the other day. And it's perpendicular. So this makes a right angle. Then it bisects the chord. So what that means is that this piece and this piece are the same. So I'll use some of those notations we used last year when we were doing geometry. This length and this length would be the same. So that can be pretty useful if we start drawing some triangles also, with a little Pythagorean theorem happening. So let's take a look at that. And this did not copy really well. I'll try to interpret it for you. It says circle P has a radius of 5 inches and PX is 3 inches. Segment PR is perpendicular to segment AB at point X. Find AB. So find the distance between A and B. So here's A and here's B, which is all the way across. Now, we know that this is a right angle right here. It's marked, but we also just know that because this and this are perpendicular, that these are going to be the same. So this one and this one are going to be the same. And this is a right triangle. So if we find this missing side right here, all we have to do to get the distance from A to B would be to double it. Now, this distance right here is not the hypotenuse. 5 is the hypotenuse across from the right angle. And so we want to make sure that we're being careful. There's also a point X in here, so I don't want to call that point X. I don't want to call it A or B. Let's call it Y. I think that's something that's not on there, so we'll call that little piece Y, just for the heck of it. So when we set this up, we'll have 3 squared plus Y squared, those are the 2 legs, equals 5 squared. So you have 9 plus Y squared equals 25. Subtract 9, we get Y squared equals 16. And then if you square root that, you're going to get Y equals 4. Some of you are also going to notice that that is a 3, 4, 5 triangle. You might remember the Pythagorean triples from 8th grade. And so anyway, so it's 4 from here to the center, and then I'd have to have another one. So 4 times 2 is 8. So if you were going to use the Pythagorean triple, just put 4 down and then show me that you're doubling it to get 8. But most of them are not going to be Pythagorean triples, and so it's not going to work that way. Okay, so we have a thinking question on the next one. It says, name 2 pairs of congruent segments. So there's more than one. We just learned that PQ and QR are the same. So I could say PQ, put the little segment bar, is congruent to segment QR, using some notation from last year. Now the radii of the circle would also be the same. So you could say PC is congruent to CR. And those are sometimes questions you'll see in like an ACT or an SAT. They just want to know if you know what in the picture is going to come out the same. Oh, and so the PC and CR are radii. You could also make that congruent to CS, because that goes from the center to the outside. You could include this whole thing as also congruent. So it says if PR is 8, so from here all the way to here is 8, find PQ. So we just take 8 divided by 2. We'd get 4. Pretty straightforward on that. Looks like a totally complicated problem, but they like to throw those in on ACTs and SATs a lot, just to see if you know what those relationships are, and sometimes you can just figure it out by using a little logic and what the picture looks like. But anyway, just throwing that in. It was an old ACT type question that they used to ask different ways on different years. All right, so let's look at this one. If CQ equals 10, let's mark that. This little piece right here, from here to here is 10. And PR is 24. So from here all the way to here is 24. Find the radius. I'm going to break that 24 in half and put 12 and 12, because I know that those are the same. And then we're going to find the radius. So you could just use the radius as this little piece right here. I'm going to call it, I can't call it C because C's in the picture. Let's call it X. And so we have a little right triangle there, and this is just a Pythagorean theorem problem. 10 squared plus 12 squared equals X squared. So 100 plus 144 equals X squared. 244 is X squared. We square root that, and it comes out about 15.6. Sometimes they'll want this in exact form, and you'll simplify the radical, but for most of these we're just going to go ahead and use a decimal, because that'll make more sense in terms of the picture. And you can look and say, okay, it's 15.6, look like it's about right. Well, it would be longer than 10 and 12, but not so long that it's impossible, so it looks reasonable. Let's look at the next one. If the radius is 9 and QS is 1, find PR. Okay, so QS right here is 1, and the radius is 9. So this would be 9, this is 9, and also from C to S would be 9. So if we take off that 1, that would make this little piece right here, from here to here, 8. And it wants us to find PR. Well, we can easily find half of it and find this piece down here. So I'm going to call that X, and then we can just double it. So I'll have X squared plus 8 squared equals 9 squared. The 9 is the hypotenuse. It's across from the right angle. So we have to make sure it's on the side by itself. So X squared plus 64 equals 81 if we do those numbers. Subtract 64 from both sides, we get X squared equals 17. And we'll square root both of those. And if you're doing a decimal, it comes out about 4.1 from here to here. So if we double that, that would tell us that PR would be about 8.2. So we just take this number and multiply it times 2. I was trying to write a times 2. Here, I'll write it over here. 4.1 times 2. And that's how we got the 8.2. So you just have to know a few things about the circles and the relationships and know that there's a right triangle there, and these are not too bad. So let's look at a different picture. It doesn't have quite as many lines in it. It says PR equals 18, so that's this piece right here, 18. And QS is 44, so from here all the way to here is 44. So we're going to chop that in half, 22 and 22, because we know from the theorem that those will be the same since they have it marked as perpendicular. And it wants us to find PQ, which I'm just going to call X. So this is straightforward Pythagorean theorem. 8 squared plus 22 squared equals X squared. So this is 324 plus 484, and if I add that up, I get 808. I square root that, and we will get 28.4 for that distance. So PQ is 28.4 if we round off the decimal. So a lot of this is Pythagorean theorem. We've been using Pythagorean theorem since 8th grade. No big deal. It's just knowing how the relationships are going to work on the circle. All right, one more. So it says JM is 24. So this right here is 24. KM is 42. So K to M is 42. So I'm going to chop that in half and put 21 here and 21 there, because we know since these are perpendicular that those are going to be the same. And then it wants us to find JL, which is this little piece right here. And so I'm going to call that X. And so I would have X squared plus 21 squared equals 24 squared. The 24 is the hypotenuse. So 21 squared is 441. And 24 squared is 576. And we can solve for X by first subtracting 441 from both sides, and you get 135. Then we square root it, and you'll get approximately 11.6. So this is 11.6. Now, I don't remember for sure, but I think on the assignment, I remember from last year, a question where it may have asked you, oh, my pencil just fell apart. They may ask you for this other little piece that goes from L to the outside, like maybe we put an N over here and this is the L. And they ask, oh, what's L in? So let's just talk about that a little bit. If we found out that this piece right here is 11.6, just this piece, this would be a radius from the center out to N. And so we would just take, it would be the same as this radius, which is 24. So we'd take 24 and subtract 11.6, and you could come out 12.4. So realize they could ask slightly more complicated questions, and what you have to figure out is that the radius is going to be the same all the way around, whether it's got other lines through it or what have you. You just have to kind of reason through that logically. So you take the 24 from this radius and figure it's the same as this radius, and then since we found that this piece was 11.6, you could subtract